Okay, so for the first part of the review, we're looking at a function and the number of people in a swimming pool and the temperature of the pool in Fahrenheit. So what is the independent variable? So thinking about like X and Y. You know, if you were to graph this, and I think there's probably a variety of ways that you could think about this. So again, I could take both ways. Like if you thought about this as like the temp of the pool, you know, the warmer the pool, the more people that are in it. Or I know I talked to some of you guys who said like the people in the pool depends on the temperature. So the more people in the pool, the higher the temperature. Again, so I would accept either answer on that one. That's kind of a tricky one. So the second one here, let the function f be increasing and decreasing, but not both. State whether the function is increasing or decreasing and justify your answer. Well, let's see, 9 to 11. Let's see if, well, let's try and graph this here. So if we were to graph this, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 goes with 8, 11 goes with 12, 13 goes with 15, 15, 17, and 17, 18. So it would be increasing, and you could say it's going up. Or technically, we could say when A is less than B, f of A is always less than f of B. Because our values here, they are increasing. So both of them are increasing there. So on what intervals is it concave up? So concave up, where is it smiling? Well, it starts smiling here and then goes up. So I would say from I to infinity. Well, where is it concave down? Well, concave down would be our reverse here. Where is it frowning in red? So negative infinity to I. Where's the graph increasing? Well, it's going up at these dashed marks. So I would say negative infinity to h. And where else does it start increasing? Is at k to infinity. So it's decreasing in between those, between h and k. Where are our zeros, our intercepts? Well, at G, J, and L. And our y-intercept down here would be at B. So the next one is a calculator one. Find the average rate of change from -5 to 1. So remember, we got to find f of -5 minus f of -1 all over -5 minus -1. So let's see, if we plug in -5, the square root of 1 minus 4 times -5. So that is, let's see, 1 minus -20, so the square root of 21. And then we have to plug in 1 minus 4 times -1. So that would be 5. So then this would be the square root of 21 minus the square root of 5 all over -4. And if you type that in, we get -0.5866. All right, our next one here. Find the average rate of change for each interval. Well, 135 and 200. Okay, so 3.5 minus 0.3 over 135 minus 200 tells us negative 0.49049 miles per second. So 24 to 135, again y is on top, 135 minus 24 over 3.5 minus 8. Type that in, we get negative 0.0405 miles per second. And the last one, 200 to 24. So 200, Oh, the second one I did wrong. I'm sorry here. The y's on top. So 3.5 minus 8 over 135 minus 24. I was going to say that didn't sound right. So this next one here, our y values on top. So we have 0.3 minus 8 over 200 minus 24. So negative 0.0437 miles per second. So estimate the rate of change at -1. So if you guys remember, to estimate at -1, we pick values on either side. So what if I did at x equals negative 0.999, and then at, you know, right around there at 1.01. So we could find our rate of change of that. So if I did f of negative 0.999 minus f of 1.01 over negative 0.999 minus 1.01. So let's go to Desmos. So let's see, parentheses, negative 0.999 squared minus negative 0.9999. So there's our first value. Then we said 2.01, so 2.01 squared minus 2.01. All right, so if we did this, we'd have 1.9997 minus 2.01. Oops. Over our x value is negative 0.999 minus 2.01. Oh, why did I do 2.01? Sorry, guys, that should be 1. Because we want it right around there. All right. So we need to change this. Something about this doesn't seem right. Because it's at -1. I keep messing up. I'm sorry. This would be on the other side. My bad. Parenthesis, negative 1.01 squared minus negative. That should probably be better, because apparently I can't read my own writing. This is why you should write things out. All right, so let's see if this makes sense. So let's talk about this. So I went back and I did values right around -1. So I did 0.999, negative 0.999, and then on the other side, negative 1.01. So I said if I plug those in, my y's over my x's, and if I do that, so I plugged in negative 0.999 into the equation, and again, that equation was x squared minus x, and then I plugged in negative 1.01 to get my y values. So we have negative 3.009. And approximately there. All right, number 7, Mr. Gardner is decreasing the amount of water used in the lawn each month, and the height of the grass is decreasing. So does this represent a positive or negative rate of change? So let's see, if we were to graph this, water, height of grass, so it started high, and now it's less water, the less height, so that is actually a positive rate of change because it's becoming less negative. because the less water, the shorter it is. All right, find the rate of change on this function. So let's do f of negative 4 minus f of 1 all over negative 4 minus 1. So if we plug in negative 4, 7 times 2 times negative 4, that would be 15, and plug in 1. 7 minus 2 times 1 is 5. So 15 minus 1 over negative 5, 15 minus 5. So 10 over negative 5 is negative 2. So from 1 to 2, so f of negative 1 minus f of 2 all over negative 1 minus 2. So if we plug in negative 1, 3 times negative 1 squared, 2 times negative 1 plus 1. Let's see, that's 1. So 3 plus 2 is 5, plus 1 is 6. And then plug in 2. 3 times 2 squared, 2 times 2 plus 1, 4. So that's 12 minus 4 is 8, plus 1 is 9. So we have 6 minus 9 over negative 3 gives us an average rate of change of 1. All right, so this just says over consecutive equal length intervals. So the rate of change. All right, so let's try f of 1, f of 2, and f of 3. All right, so f of 1, 5 times 1 is 5, plus 9 is 14, times 2 is 19, times 3, 15, plus 9 is 24. So we could look at it a couple ways. We could look at this so what is the rate of change of the average rates of change? So what is our rate of change here? So this is basically asking for the second difference. And we could look at this and we could say it's going up by 5 and 5, so it's going to be 0. What is the rate of change of the average rate of change? So we found our average rate of change. So what about this one? Let's do f of 0, f of 1, f of 2, and see what happens. So f of 0 is 0. F of 1, so that would be 2 minus 5 is negative 3. F of 2, 2 times 2 is 4, minus 20 would be negative 16. We could do a 3 if we wanted to. 2 times 3 is 6. 3 squared is 9, times 5 is 45, so 3 minus 45 is negative 39. So our first difference, it's going down by 3, down by 13, down by 23. Our second difference, down by 10, down by 10. So the rate of change of the average rate of change is negative 10. Okay, the function's concavity does not change. Determine if it's concave up. Well, what's happening here? It's going down 15, down 20, down 10, and down 4. So if we look at that, what is happening to our rate of change here? Excuse me, that's 25. The rate of change is increasing, so it has to be concave up. So again, our leading coefficients on this one and our degree. So our degree is 5, the highest power. The number out in front is 1. All right, here our degree would be, oh, that's not the highest power. Our degree would be 3. Our leading coefficient is 7. So if a polynomial function with given values, are there guaranteed extrema? So let's see, what does this mean? F of 0 is negative 3. F of 4, when x is 0, y is 4. And when f is 7, x is 7, 1, 2, 3, 4, 5, 6, 7, it's 0. Excuse me, 4, 0, 1, 2, 3, 4. I messed this up. Let's try this again if we were to graph this. Sorry, guys. When x is 0, y is negative 3. When x is 4, y is 0. And when x is 7, y is 0. So is there an extrema? Well, something it has to go through that like this or like this. So yes. So it has to be between x equals 4 and x equals 7. So what about this next one? At negative 7, 1, 2, 3, 4, 5, 6, 7, it's 0. When x is negative 2, it's up at 5. And when x is 0, it's at 1. And at 9, 2, 3, 4, 5, 6, 7, it's 0. So somehow it's got to go through all these points. So is there an extrema? Well, yes. And we don't know exactly if it's that point, but somewhere between x equals negative 7 and x equals 9. So the next one, is there a global max or minimum? Well, what do we know about this one? It's even powered, so it's like a parabola facing down, so yes. So there would be a max. Where this one, it's a bendy straw going up, so we do not know. There is not an absolute max or min. So find the absolute extreme. The absolute min, well, right here, our absolute min of 1 is at x equals 4. It keeps going up and up, so there's no max. But where are relative mins? Well, here's a minimum and here's a minimum. So at x equals negative 1 and x equals 4. Because again, a minimum is any of the low points on the graph. And what about relative max? Well, there's just one right here at x equals 1. All right, so we have to figure out where is this less than 0. Okay, well, if we factor this, this factors into x minus 5 and x minus 3. And I know it's a parabola going up, so it crosses at 3 and 5. So I know it's a parabola. So when is it less than 0? And I should say less than or equal to. So in between 3 and 5. Now if we factor this next one, I'm going to factor out that negative x. So this is x squared minus 5x minus 24. So now if I factor this, it's x minus 8 and x plus 3. So where do I know this one crosses? At 0, negative 3, 1, 2, 3, 4, 5, 6, 7, and 8. And I know it's a bendy straw going down. So it's got to go down through here and down again. And the question is, when is it greater than 0? So here and here. So from negative infinity to negative 3 and greater than or equal to, so I'll use a bracket, and then again from 0 to 8. All right, so the next one, how the degree of a polynomial is 7 with real zeros at here and has a multiplicity of 3. How many non-zeros does it have? Well, let's see, how many real zeros? 1, 2, 3, but this one has a multiplicity of 3, so that's a total of 6. So no, sorry, did I circle the wrong amount? Let's see this again. So zeros at x equals negative 8, so multiplicity 1. X equals 1, multiplicity 1. X equals 4, multiplicity 1. Oh, and x equals 1 has multiplicity of 3. Well, that's a total of 5, and it's degree 7, so it has to have 2 non-reals. 5 minus I is a non-real 0. Find another. Well, they come in complex conjugates, so it's 5 plus I. Find the degree of the polynomial. Okay, well, let's see our difference. Down 4, up 6, up 16, up 26, that's 36, 46, and that's 56. Well, I look, the difference between all of these is 10, so it's degree 2. So is this even, odd, or either? Well, I can fold it in half, so I know that that's even. This one I can rotate, so it would be odd. Well, what do we know about this? Is it even, odd, or neither? So we could graph these and take a look at it. We could also say, like, if it is even, if I plug in a 2, whatever comes out has to be the same if I plug in a negative 2. Those two have to be the same y value. Where if it is odd, if I was to plug in a 2 and a y comes out, if I'm to plug in negative 2, it has to be that opposite value. So we could test it that way as well by saying, let's pick a value to plug in. All right, 5. If it's even, a y value comes out. If I plug in negative 5, that same value comes out. Where if it's odd, if I plug in 5 and y comes out, if I plug in negative 5, it has to be that opposite value. And I'll let you guys try those. All right, so end behavior. So this is a bendy straw going down. So the limit of f of x as x goes to negative infinity, and the limit of f of x as x goes to positive infinity. Well, as it goes to negative infinity, it's going up. So that would be positive infinity. And then as x gets bigger, it's going down, so that's negative infinity. So our next one here, it's a parabola going down. So our limit of f of x as x goes to negative infinity, they're both going down. So this one, oh, sorry, and it should be p of x, my bad. P of x, because that's our function name, as x goes to infinity is positive infinity. And how about this one? So the limit of p of x as x goes to negative infinity. Well, that's on the left. It's going down. And then squeeze this in here. As x goes to positive infinity, it's going up. So sketch a graph of a polynomial that has, let's see, they're both going up. So it could look however we want it. Tons of swirls, but it has to end going up.